This is example number 2 on buckling. So this particular example, if you want to pause the video, you can if you want to take notes on this. This particular example is very similar to our previous example that we did in class. Let's just read the example. The example says that a column with one end fixed, so it's a column with one end fixed, the other pinned. I always like to do sketches. Sketches help us better understand what's going on. So it's fixed. And then you have, it's pinned on this side. It's always going to be rollers. It's made of low carbon steel. We know the material properties for this. So you always find that those material properties. 30 times 10 to the 3 KSI. And the problem is saying the column has a cross section that's rectangular, and the rectangular cross section is of width B, height is 2B. Find the dimension B such that the column will hold a maximum load of 20 kips and a design factor of 2. So we know the first thing, you know that your actual length is 18 inches and that your P critical is going to be the design factor times the load. So he's saying it's going to hold a maximum load of 20 psi kips. So when he's doing that, you know that your real load for which you're going to do your analysis for will be your design factor multiplied by 20,000, and that would give you 40,000 pounds. So that's the critical load. So your column needs to be able to, it's not P critical, so it's the P for the analysis. So when you would do the analysis, your analysis needs to be able to hold this amount of load. Okay? There are 2 ways to do the analysis, but this is one of them. It's easier to do it like that. The next thing we want to do in the problem is we can come here and you can choose the option, and we only talked about this in the previous example. This is the option fixed pin. And for this case, C is equal to 2. L is equal to 18 inches. That means that LE will be L divided by square root of C. And that would be 18 inches square root of 2. And that gives me an effective length of 12.73 inches. Okay, so with that said and done, now we go ahead and we start our problem. The very first thing I need to do in this problem is, as we always do, we always find your slenderness critical ratio, and that ratio is equal to 2e pi squared sigma yield. Note that there's a c missing there. And when we calculate this, I get 117.35. It is dimensionless. Now we have a problem. When I calculate my RA, my actual slenderness ratio is LE over K. And I do know this, but I do not know my K. But I know that the radius of gyration. Radius of gyration is equal to my inertia divided by A. For this particular problem, your area is equal to base that's B, your height that's 2B. So that would give you 2 times B squared. You have your inertia, that is base times height cubed divided by 12, and that would give you 2b to the 4th power divided by 3 if you simplify all this. Then your k is nothing else than the square root of 2b squared, b to the fourth divided by 3, and divided by area, that 2 times b squared, and that would give you b over square root of 3. And from here, then what you have is RA is equal to 12.73 divided by b over square root of 3. And then if we replace all these numbers, get this value. Okay, now look what's going on. In this particular problem, if I draw my plot here, and we know that your plot of your stress versus your L over K, if I plot this, okay, and I have this, my critical slenderness ratio, and we can agree that depending on the side that I'm working on, if I'm working on this side, if your RA is bigger than RC, then in that case, I will use my Euler's equation. If I'm working on this side where your RC, or equal, right? It can be equal to, your RA is equal to RC, but bigger or equal than 10, then I'm going to use the J.B. Johnson equation. Okay, but the question is, I have no idea, because depending on the value of B I choose, I'm either on this side or I'm on the other side. So there are many ways to do this problem. The easiest way to do it, and that was my approach, let's assume what happens if I'm on this side first, and then we will check and make sure this ratio is applied. If it's not, we'll come on this side, solve the problem, and make sure this ratio is satisfied. Okay? So with that said, let's do that. Let's do the first guess. Guess number 1. And it says, let's assume that RA is bigger than RC. It's a guess. So basically what we are trying to do is, we are saying, I got my slenderness ratio, my actual slenderness ratio is on this side. Okay, so then your equation is P is equal to AE pi RA squared. This is one of the variations of the equations I gave you last time. And so we replace all the values in there now. This side is 40,000. This side is area is B squared. This is 30 times 10 to the 6. Then you have pi. And then you have 22.05 over B squared. And if you simplify all this, you find that it says 40,000, 12,17,962 b to the fourth power. And so we solve for b from this equation, and we find that b is equal to 0.426 inches. Straightforward, divide on both sides by this number and take the quartic root, square root of that. So then in the problem, I know that my RC was equal to 117.35, and my RA in the problem there, which I need to always check, you can see that would give you 22.05 divided by 0.426, and that would give you a value of 51.79. Note that this value it contradicts my assumption, So this is not correct, and actually it is bound by my actual slenderness ratio is bound by these values, where this is 117.35 and this is 71.79. So it's bound by these values. So that means that my second guess will be, let's go to my J.B. Johnson equation for my second guess and see if that works out. Okay, so now I go to number two. And the J.B. Johnson equation says P is equal to A times sigma yield minus 1 divided by Young's modulus, sigma yield, so the actual slenderness ratio, 2 times pi, all of this squared. And then on this side I have, on this side we have 40,000. And then this is B squared, that's your A. This is 43,000, that's your strength, yield strength. 10 to the 6, 43,000 divided by 2 pi. Your RA is 22.05 B. This is squared. So what you can see in this problem, this is a very complex equation. You can try to solve for B if you got a good solver, or you want to do it by hand, you want to have fun, sure, you can do that. But my way of trying to solve this problem was a lot easier. So what I did was I said, what happens is B is equal to 0.1, right? If I set B equal to 0.1, let's see what happens. I find that on the left-hand side I have 40,000. On my right-hand side, I got 680. This is bigger than this. They are not equal, so I need to keep iterating. So what happens is this is 0.2. Then it's 0.2, I got 40,000, and then I got here 3440. And this is still bigger than 0. This is still bigger, right, this value. Then I'm going to keep iterating. Now I can, and as I iterate, I find the following. So what happens is, when I take B equal to 0.6, you see your left-hand side is 40,000, right-hand side is 30,960. And then when B is equal to 0.7, you get 40,000, sorry, is still bigger, they're not equal. And then 40,000, you get a value of 42,140, and now you realize this is bigger than this value. So no, you know that your answer has to be bound between these two values. And I am going to jump some steps here. And if I just give you B is equal to 0.68, I did a couple iterations here. I can show that 40,000, and I get on the right-hand side 39,766. If I take B equal to 0.69, I get 40,000, and on this side I get 40,946. So what you can see in the problem is this is less than 0, this is bigger than 0. However, this value is going to exceed, and you don't want a third decimal point because that's not feasible. So this one is not acceptable. It went over. We want to have a value that, I think I put this opposite the other way around. So this is bigger. Sorry. This is bigger and this is smaller. There you go. And so this is the value that I'm looking for. So the solution to the problem will be B is equal to 0.68 inches. And we have to double check again your actual slenderness ratio 0.05b, and you can see that value you get is 32.32, and it is indeed bound by this value. So this example is a very good example where you have to start with the initial guess. You start with initial guess, and then at the end of the day, you may have to change equations. That's actually what your MATLAB code in a way does. However, you have to watch out when you use the code. You may have to make some slight modifications to it before you use it as it is. So this is your final answer. This is the solution for a maximum load of 20 kips and a design factor of 2. This is your solution. This is what we were actually looking for. So these problems, as you can see, they're not very complicated. We just have to be very systematic and go one step at a time, understand what's going on, find the right equation, right-hand side or left-hand side, and then replace all the values. Here I found my B, and I realized that B actually makes my R violate my condition. So therefore, I'm not on this side. I should be on the other side. And then this you can do as simple even in MATLAB or in Excel, where you can put a bunch of values of B, keep modifying until you get to a close value that you're within a range. So that's how I did this solution. And this completes exercise example number 2.